Welcome to the video recording of partial application and pattern matching for Xamarin University. My name is Glenn Stevens and I'll be taking you through today's course. Now before you begin, there'll be a number of exercises that we'll be going through, so you should have downloaded the class materials from the university.xamarin.com website. Alright, let's get started. We've got several things to talk about today. We're going to be quickly looking at some of the core functional aspects of F#, things you've briefly seen in previous courses but haven't really completely explained. Then we'll be diving into a very useful feature of F#, and that's pattern matching. Let's start by covering some of the functional aspects of F#. And in some cases, this will be just a reminder of things that we've already seen a little bit of before. And we'll do this in 3 parts. First, we'll look at how functions are composed with pipes. Then we'll look at a specific type of discriminated union that's built into the language called an option type. And finally, we'll apply a specific pattern that we use in F# called partial application, which is used to compose functions together, creating high-level functions that are easier to use. We've been positioning F# as a functional language from the beginning, and that's true. It sits on the shoulders of other functional languages and draws quite a few features from them. And it's these concepts we specifically want to look at first. However, it's not a purely functional language. It sits on the .NET framework, which was designed and exposes quite a few concepts from the object-oriented world. And as a first-class citizen in that world, F# also inherits quite a bit of capability that's decidedly not functional that you can use. Our first functional concept is pipelining, and this is where we take the output from the pipeline and apply it as the input to the function. And it's similar in nature to Unix pipes, where you'd commonly pipe the output from a command line tool either into another tool like grep or to a file or some sort of formatted output. In some ways, there's nothing special about pipelining. For example, examine the code presented here, where we call list.sum on a filtered list of values from 1 to 10. And you'll notice that we have to surround parameters in parentheses to ensure that they're evaluated properly and passed in. And this results in the value 30, as you can see. Instead of passing parameters, you can use the forward pipe to write the expression more naturally so the evaluation order is more obvious. And there are 2 primary benefits to this approach. First, as you can see here, the reading order is often superior when using pipelining. So we'll take the array and send it to the list.filter, then send the result to list.sum. And that can be easier to understand than apply list.sum to the result of applying list.filter to the result of this array evaluation. And second, type inference often works much better for the pipeline version. And this is probably the biggest reason that pipelining is used so much in F#. The forward pipe operator is the most common pipelining style that you'll use, but it turns out that F# supports a backward pipe operator as well. And the backward pipe operator allows us to evaluate an expression and then pipe it backwards into the preceding function. And this can preserve the call order when the important expression we want to focus on is the leftmost part of the expression. And as an example, take a look at this code here where we're calculating the distance between 2 points by taking the square root. And in this case, we're forced to surround the inner call to the defined square function with parentheses so that F# evaluates it first and then passes the result into the square root function. And we can then clean this up a little bit with a backward pipe operator. And notice that we no longer need the parentheses. And because it's a backward pipe, F# will evaluate the result of that expression and then use the result as the input parameter to the square root function. And using these operators is totally optional, and they're really a shorthand that many programmers find more intuitive and easier to read. However, if you prefer to use a parameter syntax instead, there's really no difference in the generated code. Another interesting feature that you'll find in F# is the option type, and this is a predefined discriminated union with 2 known values, sum and none. And the sum keyword is used to represent the presence of a valid value, whereas the none keyword is used to represent an invalid or missing value. For example, in the second code fragment, we define a new function named doubleval, which will return the input numeric times 2. However, we only want to allow for positive non-zero values. So what should we do if you pass in 0 or a negative number? Should we return 0? Should we return the input? And that's the purpose of none. It provides a language standard for something that's not valid, which you can then test against. And F# uses option types all throughout the built-in functions to indicate failure, for example, when searching a list. And you're encouraged to use this feature to report input errors instead of exceptions, unless the program can make no forward progress without the input. And the options module has several built-in methods as well to test for option types. There's option is none, option is some, as well as methods to perform filtering and iterations on option type values when they have a value. So things like option.map and option.iter, which you'll look at a little bit later.
So let's begin work on our first lab. So now pause the video, and when you've done everything, then resume the video and we'll review the contents.
Okay, let's review the first lab. Now you should have created an F# library project and created an appropriate script file. I've got one here, I've just called it lab1 FSX. I'm going to take a copy of the list of option types together, and we can then add the ability to filter the list using the isSum function on the option type. So we'll get our results here from the list, and then we'll pipe it through to the list filter function. And for each entry in that list, we'll be using the isSum on the option type. We'll then get the values from the option types we know have a value as a result of applying that filter. So we'll use the list.map, and based on the function, or based on the value of the function, we'll actually get the direct value itself. And then we can sum the entries to get the result, all using the lovely pipelining. So let's run the code in the REPL. We'll select all that code. We'll send the selection to the REPL. And here we can see the result. Another native language feature that you'll use quite often is higher order functions. And this is where we pass a function as a parameter to another function. So in other words, higher order functions treat other functions as data input. You see this in C# as well. Link does this quite often, however it's central to F# programming and almost impossible to not use when building applications in F#. So let's look at the mechanics and a few examples starting with returning values from functions. And when you create a function in F#, there's no explicit type definition for the return value, and you don't have a keyword to define the return result. Instead, F# takes the final line of the function and then uses that value as the returning result. As an example, take this getData function defined here. It's a slightly modified version of the one we examined earlier, taking an input array, filtering it, and then returning the sum. And since the list.sum is the final expression, the result from that expression becomes the return type from the defined function. And this generally results in more concise code that once you get used to it can be easier to read, since there's only one place to look for the return value, unlike C#, which allows you to define multiple exit points from a method definition. It's very illuminating to examine the return type signature from a function in F#, and most of the examples we've used in the past take a single parameter, but when you include more than one parameter, something interesting really happens. Here we have a multiply function which takes two numeric values, presumed to be integers, and then returns the product of those two values. And if you type this into the REPL, you'll get a type signature back that looks like this. And you'll notice that it looks by the type signature to be a string of functions, where each one takes a single parameter. And this is because F# performs something called currying on the function definition. And all F# functions are displayed as curried functions. And to understand why it does this, we have to introduce another important concept in F# called partial function application. So let's start with a simple case. Just like in C#, we can take defined methods which have a set number of parameters and then utilize them in other methods, wrapping them to make them easier to use. So here we're defining a new double method that takes a single value and then reuses our already defined multiply method to multiply the single input value by 2. And this is, in effect, a manual currying of the multiply method for a specialized case, which is doubling a value. And we call this programming pattern partial function application, or sometimes just partial application. And this is where we fix one or more of the parameters to a more generalized function by providing a more specialized form. And you'll find this technique all over F#, particularly in the libraries. So now let's just see where it gets really interesting. And because we can pass functions in as parameters, it turns out we can take our multiply method, fix one of the parameters, and then pass that resulting function into another function like list.map. And this will take the input list and use each value contained in it as the second parameter to the multiply function, as you can see here in the output presented. And this is incredibly powerful as it allows us to compose complex expressions quite easily in ways that C# just can't match. Now let's begin work on the lab exercise for partial application. Like before, pause the video, complete the exercise, and we'll review it once you've finished.
Okay, let's review the second lab. And our second lab looks at using partial application. And we're going to start by looking at the functions that we're going to use. We have the list difference and also the Minkowski function. And the list difference is really designed to calculate the difference between two values, and the Minkowski function is really geared towards calculating the distances between 2 points. A lot of people, when they do this exercise, get caught up in the maths of the Minkowski function, but the important thing really here is that we're demonstrating the partial application mechanism. So I want you to look at the parameters of Minkowski and see that it takes 3 parameters. We've got P indicating the power, and list X, and also list Y. So we're going to use that information in our Manhattan function, and we're going to define the Manhattan distance function as a partial application pattern by calling Minkowski with the first parameter P set to 1. So Manhattan distance, by the way, really calculates the number of blocks that you have to navigate. So here's our implementation of Manhattan, which is really Minkowski with a p-value of 1. So when we call Manhattan, we only need to supply the additional parameters, list X and list Y. And you can see that's what we're doing here as well. And that gives us that partial application mechanism. Likewise, the same thing is happening for the Euclidean. Euclidean is really just Minkowski with a p-value of 2. And we're passing that value in directly. So when we call Euclidean, we only have to pass in 0.1 and 0.2, which will be the list X and list Y values.
So you've just seen some of the functional features of F# and looked at some concepts like currying, option types, and partial application. The next thing we're going to focus on is pattern matching. And this is a fairly deep topic that we're going to really only start to scratch the surface of. And pattern matching is really powerful in F#, and you'll find it used in a variety of places. And we'll try to break it down into some simple cases and then show you a few of the most common pattern matching styles that you'll use most often. However, make sure to read through the MSDN documentation. It has complete examples of every form of pattern matching that you can use in F#. First, let's define what pattern matching is. And it's very likely that you've used some form of pattern matching in your programming career. So deliberate filters or even higher level tools like regular expressions. Pattern matching is really about decomposing structured data, that is, extracting values of interest and taking action on them. And in F#, pattern matching is built into the language and can be applied to discriminated unions, to types, constants, records, and a variety of other constructs. And it's most often used to provide some kind of transformation on the data that's being matched. And the syntax is really quite simple. And every pattern match in F# will follow the presented form. You'll have an inbound expression being matched and then 2 or more patterns which, when they're matched to the expression, will provide the result. And again, that result is often a transformation of the input expression. And F# matches the patterns top down, much like a case statement. And if there's multiple matches, then only the first match will be used. And often you'll find the final match to be a wildcard match, represented by the underscore. This is always the final pattern and is used as a fallback when no other match is located. So let's break this down with some simple examples. Here we've defined a new function called divisible by 3. And this function takes a single numeric value and should return a true or false result. We could define this with just an expression, but it provides a very simple introduction to the pattern matching syntax, so that's what's been done here. And first, The pattern match starts with the match keyword, and this provides the expression to evaluate, in this case x modulus 3. Then we have the comparison values, each on a single line starting with a parallel bar. And there are 3 comparison values provided in this example, 0, 1, and the wildcard match, which is always last. And each comparison line also has an expression result, which is our returning value when that comparison is a match. And you can also add an expression which is used as a condition on the pattern, and this is called the pattern guard in F#. And this is done with the when keyword on the comparison value. So in this example sign function, we're returning 0 when the input value is 0. Then we take the input value and compare it for less than 0 and greater than 0 and return -1 or 1 respectively. And the pattern guard is useful when you have some expression that you want to use for the comparison rather than a constant value that you're comparing it to. If the pattern match result doesn't use the input values, then you can shorthand the syntax by just using the function keyword. Here we've got a pattern match looking for either an x or y value that's 0. And the result expression that's returned doesn't use the input point, and so this would be an example where we could reduce the typing. And this definition is equivalent to the other one, and you'll notice that we still have the same pattern comparison values, and the only change is the removal of the match and the with keywords. So let's talk about the types of patterns we can match against. And F# has quite a few available. We can match against constant patterns, discriminated union patterns, tuple patterns, records, lists, and arrays. And we can also combine comparison values with the AND pattern and reduce our matches with the OR pattern. So let's examine some of the more common types that you'll run across. You've already seen examples of the constant pattern match, and this is where we explicitly specify the value we expect. The constant comparison value itself can be any string, numeric, or literal value, similar to the C# case statement restrictions. And in this example, we're matching against 2 parameters, a website URL and an agent ID, turned into a tuple and returning a true-false result based on whether we think the input is a secret agent or not. And if the website's www.control.org and the agent ID is 99, then clearly she's a secret agent. And if the website's www.chaos.org, then no matter what the agent ID is, it's going to be a secret agent too. And if the agent ID is 007, no matter what the website is, again, it's a secret agent. And finally, we have our wildcard match, so any other combination will just return false. We can also do pattern matching on discriminated unions. And remember from our earlier class that a discriminated union is a union of closed values where I can choose one of the values. And in this case, I'm creating a discriminated union for a shape where I can define a circle with a double radius, a triangle with 3 side lengths, and a rectangle with a width and a height. And I can pattern match against the shape as you can see here in the code. And we match against the selected value of the discriminated union first, so circle, triangle, or rectangle. We can also capture the field values assigned to each one with named placeholders and then use those placeholders in the result expression to calculate the area for the given shape. You've seen this already, but we can pattern match against tuple values, again supplying some values as constants and others as named placeholders, which can then be used in the resulting expression value. Finally, we can match on records, and here we define a new record for a person and then provide a function which takes a person and a string name to match against. And when the name is matched, regardless of ID, which is using a wildcard match in this case, we return true. Otherwise, we're returning false. And you'll notice that we use a pattern guard here in the form of the when condition in order to match against the name placeholder from the comparison. And when we use this, we can pass in the defined person and a string and get back either true or false. And often when performing pattern matching, we'll have multiple patterns that return the same values. As an example, here we have a valid point method, which is looking for 0 coordinates and returning true or false results. And notice that in 3 of the cases we return false, where either x or y is 0. And this is a perfect case for the OR pattern. The OR pattern allows us to provide a single result for multiple patterns. In this case, it looks like this. And you'll notice now that we've reduced it to only 2 matching cases, but one of them have 3 different conditions. And the conditions are separated with a parallel bar to indicate an OR and have a single result expression associated with them. And here we'll return false if any of the conditions match. As you might expect, we have an AND pattern as well. AND is primarily used to provide both a pattern match and a named value to use in the result expression. So as an example, consider the code fragment that you can see on the screen. We want to use the XY values, but also pattern match them to constant 0 values. To do that, we must provide 2 expressions, one for the named value definition and one for the pattern to match against. And the single ampersand is used to separate those 2 matches. We can also pattern match on one-dimensional lists and arrays. Here you can see a list being used, but you could substitute the array syntax with parallel bars for an array. And it turns out that this feature is really only useful in limited scenarios because we have to know how many elements are in the list or array, and we have to match them in order. It's more often used to match against empty arrays rather than non-empty ones. For lists, we can also use the cons operator to match against the head and tail of the list. We use the cons operator to provide a named value for both the head and tail. And here we're testing for an empty list first, but if it's not empty, we separate the head, which is the first element, from the tail, which is all the subsequent elements, and print the single head node, followed by a recursive call to the print list function to print the remainder. And one last thing about pattern matching, always watch for F# warnings on your match expressions. F# will try to verify that all cases are covered, and when it can't, it'll issue a warning, even supplying values it thinks aren't matched. And sometimes they'll be erroneous, where you're dealing with a closed set, but sometimes these can point you to a possible hole in your logic. And this is really important because if we run across input that can't be matched when the code executes, it'll throw a runtime exception. And this is one of the reasons that most of the previous examples always had a wildcard at the end of the conditions list to be a catch-all for any matches that couldn't be handled by more specific cases. So let's try out a pattern matching exercise together. Now let's work through a group exercise where we look at some of the common F# pattern matching techniques. So let's look at the initial version. Now our core aim is to be able to convert these if-else, else-if statements to using pattern matching. So here we can see the initial evaluate function taking an array as the first parameter. And you can see the nesting that's going on with the if statements, especially where the maximum from the array is greater than 4. And it actually looks quite dense from a code perspective. So let's actually run the initial copy of this function to see what we should expect. And then we've got the values coming through in the REPL. So let's review the next part where we convert this to using pattern matching against the array. So here we're using the match keyword on the myArray parameter and initially checking for an empty array. So we're using the pipe symbol for each of the options and also using the pattern guards to check for details on the arrays, as well as using the double ampersand to get the details collating together. And you'll also notice that the size of the function has gone from 11 lines of code down to 7. And it's also easier to read due to pattern matching's top-down nature. So let's execute this code in the REPL too. So we'll send that to the REPL, and we can see that we're getting the same values again. But we're getting the same effect with less lines of code. And in fact, we could probably even simplify this code a little bit more by just using the function keyword. So take it down to 6 lines of code. And then you see it executing again. Now our next part of the exercise is to look at a version that uses tuple pattern matching. So we're constructing a tuple with the details about the array and then matching on the tuple. So you can see that in many of the matches, we're only using some of the information. So we're using the wildcard character. So for example, in this pattern match, we're only interested in the length. So we're not really worried about the maximum or the average. And like all good pattern matches, we're also ending on the wildcard. So we're capturing
all cases here as well. So let's run this code in the REPL. And again, we can see we're getting the same values come through again. Now let's review our last part of the lab. And here we're pattern matching on a list and trying to return a tuple indicating the position of the number 2 within the list, as well as the length of the list. And we're only interested in lists that have up to 3 items. So you can see we're matching on the list, looking for an item in the first position, and using the pipe symbol to indicate multiple options when it's in the first position. So just when the list length is 1, 2, or 3. Likewise, we also have the wildcard match, which will capture any other configurations. So let's run this in the REPL and see what we get. Excellent. We've got some test values here that are coming through with the right results. So this first one, it's in position 1, the length is 2. Our second test, it's in position 2 and the length is 3. And our third test, don't have the position 2 in there at all because it's not matching on those specific lists, but it's certainly returning 0 for the position, and the length is returning the length, which is 6. So there's our review for Lab 3.
So let's test our knowledge with a small flash quiz. Question 1. How would you rewrite the function below to use the backpipe operator? And the answer is A. Question 2. The when clause, A, is used to create a pattern guard, B, is used to start a pattern match, or C, is handy because it reduces the need for parentheses. And the answer is A, is used to create a pattern guard. Let's work on an individual lab for pattern matching. Again, pause the video while you do the exercise, and when you're finished, we'll review it.
For our fourth lab, we're looking at how we can work with discriminated unions to supply pattern matching on the services. So in our F# library here, you can actually see the completed solution. You can see here that we have the option types created. We've got the breakfast, the commute, and we've also got a record here that represents the routine, and another discriminated union showing the days. Now we then have some pattern matching showing us all the options we can use. We have a pattern match on the get commutes. I'll just show for that. Get commutes for day. We also have a get day for week. That it's taking the input and then doing a pattern match. And you can see the blue underline under the match condition. And the reason the blue underline is showing is because we don't have a wildcard match. So if you just do a subtle change to make sure you've got the wildcard match, so I'm just changing the 7 to a wildcard match, and that's making the F# compiler a little happier. And we'll do the same thing for the get commutes for day, and also the get breakfasts for day. So that's getting our options for us. So the next step after that is we're creating lists based on the days of the month, and also calculating the days, commutes, and breakfasts as well, based on those maps. So the get day of the week, passing in the days of months, and it's returning the appropriate match using that get breakfast for day, get commutes for day example. And then once we've got those lists that represent the day, the commutes, and the breakfast, we're using the zip3 function. Zip3 is going to make a new list that consists of 3 tuples or triples containing a day, a commute, and a breakfast. So let's run the script in the REPL, and we should see the output. It's creating that list and then printing out the schedule for each day. And then we can see our lovely schedule.
So we've just had a look at pattern matching. We've had a look at plenty of examples of how to use pattern matching in your own applications and some of the different types. And you'll get used to this as you develop more and more F# applications. In this final objective, we'll look at active patterns, a way to partition and subdivide your data. And we'll start by defining what active patterns are and what they're good for. And then we'll look at 2 different styles that you can use. And finally, we'll do a quick exercise to try some patterns out. Active patterns are functions designed to partition data into named groups, which you can then use in pattern matching expressions, just like a discriminated union. And defining an active pattern function allows you to decompose your data in a customized fashion, so you can decide exactly how the data is going to be partitioned. And the syntax is similar to a regular function with two differences. First, the name of the function identifies the name of the partitions you intend to create. And second, the identifier name is surrounded in parentheses, as you can see in this syntax example. So let's look at a real code example to see how these are defined. And here we're defining an active partition function to determine whether a person is a child or an adult based on their age. And you'll notice the name of the function has what's called banana clips around the edges, which is really a special syntax that has all the partition names separated with vertical bars, with the whole function name surrounded by those parentheses and vertical bars. So they're referred to as banana clips because they look like the banana hair clips that you often put in your children's hair. And on their own, active patterns aren't really that interesting. To make them really useful, you want to combine them with pattern matching. Here we define a new function canVote, which takes a person type that includes an age. And based on the pattern match for the age, we'll either allow them to cast a ballot in the upcoming election or not. And you'll notice that we don't need to call any method. Instead, that's done by F# implicitly just by using the match type as a comparison value. And I think you can begin to see the power of this filtering capability. So let's explore it a little bit more before you try your hand in a lab exercise. And there are actually two types of active patterns, complete and partial. Active patterns can partition the data into 1 to 7 specific groups based on the function, and complete active patterns fully specify all the groups allowed. As an example, here we've defined an active pattern to take a month and group it based on the quarter. And you'll notice that we're using a match expression as our evaluation function, and then using the OR operator to identify the month and divide it into a specific Q1 to Q4 value. And match expressions are expressions like any other and return a result. We can then use that in a pattern match expression to take a given date and then match it to a known quarter, in this case to define our goals for each quarter. And the important thing here is that we've classified our data into 4 predefined buckets, and every piece of data we flow through this complete pattern will have a known bucket. And the second type of active pattern is the partial active pattern. Active patterns that don't always produce a value are called partial active patterns, or sometimes incomplete active patterns. And they'll always have a return value that's an option type. And this type of active pattern allows you to partition only part of the available data and return no value for the portions that you're not interested in. So to define a partial active pattern, you use a wildcard character, the underscore, at the end of the list of patterns inside the banana clips. And the comparison functions should include a case for non-matching elements, for wildcards or else statements that are often used for this, and then return none. So here's a great example where we take a string as input and classify it as an integer or not using the built-in int32 try-pass method. And this actually has a couple of interesting things in it. First, you'll notice that we have the wildcard character at the end of the matches, and this is what makes it a partial active pattern. Next, we use a match expression against int32 try-pass, but we only pass in the string, and that method's also supported to have an out parameter for the converted value, if there is one. F# is uber cool with this. It'll recognize the out parameter, create a temporary value to hold it, and have the method return a tuple with the Boolean result and the out parameter as a single value. So we can then compare the first value from the tuple to determine if it was successful and put the value into our integer partition or not based on the value. We could do the same to create a float variation, and this approach is common when using partial active patterns, as it allows us to partition the data using completely different algorithms for each named group. Then we can combine these two partial active patterns in a single pattern match. Here we're defining a method named printValue, which will take an input string and, based on the type from the partial active pattern, print it as an integer or a float. And you'll notice that we're capturing the output value from the group. In other words, INF will be an integer value and floating point value coming out of our partial active pattern, not the string input. So let's see how well you know this through a flash quiz. Question 1. The function keyword, A, is only used with active patterns. B, is used as shorthand when writing pattern matching functions. Or C, is the only way to write a pattern matching function. And the answer is B, is used as shorthand when writing pattern matching functions. Question 2. Which of these functions is an active pattern? So is it A, B, or C? And the answer is C.
Let's take a look at how we can apply active patterns in a lab exercise. So once again, it's time to pause the video and we'll review the exercise once it's completed.
For our last lab of the day, we're going to be using one of the most awesome features of F# type providers to process a list of flight entries from a CSV file. So we're going to add the NuGet package F# data into our project. You'll actually see that I've already done that here. I've added the F# data. And then I'll also need to reference the assembly from our script file. So I'm referencing that with the #r because I'm in a script file, referencing the packages and the appropriate version of that library. Now after that, I need to open the namespace. And once we've got that, we need to pull in the data from the CSV file. And you can see here we're using the CSV provider. And we're reading from the SFO passenger data.csv file, which has got a lot of data in it. Now once we've got that, we're actually converting that type provider entry, which is a sequence, to a list, and we're going to use that list and process the data. So here's where we're actually defining our active patterns. We'll define a partial active pattern for December based on the input that we're receiving. In this case, it should be a string. So we're looking for a match where it ends in 12, and if it ends in 12, then we're going to say that we're returning a value of December. Otherwise, we're returning the option type for null. Likewise, we also have the deplaning function. We're looking for entries where the input is deplaned and then returning an option type of deplaning, otherwise returning none. So we're then going to pull the data from our type provider, and this is kind of the cool thing. And you'll notice that we can also use IntelliSense on that type provider to see all the CSV columns, which is quite incredible. I think the amount of effort that you have to go to bring up CSV entries in other languages is really quite intense, but type providers make it so much easier and just put all that beauty into the IDE. So we'll learn more about type providers in our next class. But you can see here in the first partition call, we're extracting all the entries where it's December based on the input from the activity period column. And that results then partitioned by looking at the entries where the activity type code has a value that indicates that it's been deplaned. And then we're getting the minimal arrivals using the list min by based on the passenger count. So let's run this in the REPL. So we can see the minimum arrivals here, and then we're actually showing the operating airline from that. So we'll select all that code, send that to the REPL. And we can see the details. So we see all the variables that have been defined, like December and December deplaned. And then the min arrivals. And then the result, which is the airline itself, ServsAir.
So we've just had a look at active patterns. We've had a look at the different kinds of active patterns. And we've seen how to use them effectively with a flight itinerary in our lab exercise. So congratulations on completing another F# course, and you've certainly learnt a bunch of new concepts for F#, and by this stage you're probably starting to get really familiar with the concepts. Now, our final class in our current F# series is looking at type providers, and you got a taste of using type providers in that last lab exercise. So hopefully we'll see you on that next class. Well, thanks everyone for attending this course on partial application and pattern matching for Xamarin University. My name's Glenn Stevens. I hope to see you again in some other classes.